The prerequisite for attending today's session is that you must have used SUMO, because we would talk about model development in SUMO and use the interface a little bit. And a prior knowledge of that will usually help. Or you must have attended our previous webinar, but no worries if you haven't. We will provide a link. We are providing a link which you can review at your own time, sometime later. Recordings and slides of this presentation will be provided after the session, sometime hopefully today or tomorrow by latest. If you have any questions during the webinar, please feel free to include them in the chat window, and our Dynamita team is standing by and they will be able to answer some of your questions on the fly. Follow us on LinkedIn and YouTube. Download, learn how to do model development in SUMO and have some fun. And if you have any questions, please contact us at support@dynamita.com. And I would again emphasize, if you have your mic switched on, please switch it off so that we can avoid any disturbances. Okay, so let's begin. Again, welcome everybody. My name is Tanush Vadhaman. I am in the Dynamita office of Toronto, Canada. And a little bit of background about myself. I've been working with Dynamita for over 6 years. I have experience in modeling, municipal and industrial plants. My background, I come from DC Water, where I did my PhD and postdoc, and worked with a lot of fun technologies such as CAMBI, thermal hydrolysis process, anaerobic digestion, high rate activated sludge treatment, and many more. So today I will be your speaker, and I would introduce you to model development in SUMO. So the goal of the webinar today is to introduce the audience to the model development capabilities in SUMO, to show you a couple of examples, to show you how we are promoting innovation in the field of process engineering and model development. And hopefully you will be able to learn from it and apply it in your own process field. A little bit of introduction about our team. We are total 11 people spread all over the world. Our boss, Imri Takas, and most of our team, which you see here, is present in the call today and will be able to answer your questions, like I said, from the chat window. We have extensive administration and programmers as part of our team, and we have a big process engineering and modeler team, which means we are quite big in terms of providing technical support to our clients. We have over 100 years of combined experience in modeling and process engineering. We have done multiple projects in the realm of municipal and industrial wastewater treatment. Turnaround time in terms of providing technical support is quite quick. And we have done various model-based projects and consulting projects and research projects. Just to give you an overview of how we are spread around the world. The map on the right-hand side, the world map on the right-hand side you see, are the licenses of SUMO, which are spread around different countries. So you can see that in last few years, we have gained dominance in a lot of countries, and we are increasing in terms of size and in terms of sales. The left-hand side map dictates how we are spread around the world. So we are 11 people, like I said, spread all over the world. And I am today talking from Toronto, Canada. So what is the goal of SUMO? What is the vision we have? SUMO is an open source process code software, meaning that you can actually, it's not a black box. You don't have to press a button and just get the answer. You can actually look inside how the model is built, how the equations are written, and even contribute by developing your own models. The open source structure helps you improve your in-house knowledge. It improves your ability to design because you understand the mathematics or the model much better. And it helps you better support your clients, and it helps us support our clients much better. So the open source and easy to implement models in SUMO allows you to quickly convert models from theory to practice. It improves model commercialization of your new technologies, and you're only limited by ideas, as you will see, that how easy it is to develop models, and having that power on your fingertips can really help. In today's world, the process technologies which are being implemented around the world is increasing. The adaptation of new technologies is increasing. So in order to support the implementation of new technologies, you need tools. Consultants need tools to design, utilities need tools to verify, to evaluate, to optimize, and to understand the technology they will be implementing. And SUMO has allowed for accelerated growth in process model development to support the process technologies which are being implemented. Before SUMO was introduced into the market, there were model developments all around the world, but getting them into the commercial world was a little bit difficult or took a lot of time. But SUMO has accelerated the growth in terms of process development. So what can you do in SUMO? You can develop new processes which can be implemented in the biokinetic metrics. You can develop new technologies such as new reactor type, or even implement a new process like in biokinetic model and in the process units. If you want to introduce new engineering calculations specific to a model file, you can do that in a plant-wide calculation file in SUMO. If you would like to implement a new control logic or introduce a new control setting, you can do that by modifying our process unit, developing your own process unit, or implementing a control logic in the plant-wide calculation. And finally, if you want to create design tools for yourself, for in-house use, or for your clients, you can implement them in the process unit as well. The system settings which you see is a separate Excel sheet which allows you to introduce special unit conversions, special solver settings, and introduce more functionality which you can add to the software. Now, who uses it? Utilities have been using this to investigate new process implementations and develop new processes, new biokinetic matrices, such as for two BioP population model. Consultants have been implementing new technology for their clients. Researchers have been using SUMO for investigating new process development. Modeling firms have been using it to develop specific models for their clients. And technology vendors are using it for in-house knowledge to understand their technology and to promote and improve and promote their technology in the market. So just to mention a few of our clients, and the list is big. Utilities such as DC Water, HRSD, and Clean Water Services have been instrumental in developing new models and are in forefront of developing new models to understand new processes, and which has speeded up the implementation and process development. Consultants such as Jacob and Black & Veatch are using SUMO to develop new processes, new process units for their client, and provide support. And finally, the bottom four which you see are technology provider examples, such as Kurita Water Industry, Smith & Loveless in US, IM Team and Ovivo are also instrumental and in forefront in using SUMO in terms of developing their own technology and trying to do in-house design and provide support to their clients. So the list you see on the right, such as greenhouse model, or A stage, which is an adsorption, high rate activated sludge model, advanced anaerobic digestion model, mobile carrier, and I'll skip over some of them, are being developed by these clients for their in-house and for their client support. And there are just too many to list. And this has been possible just the way engineers are able to develop models in SUMO, and they are able to test the model quite easily before which can be commercialized. Okay, so the most important point after it being open source is, how can engineers develop models? Do they need to know C++? Do they need to know any other programming language? No. So in SUMO, what we have developed is a pseudo language called SumoSlang. It's a modeling language where the equations are written in Excel. And we have created a SUMO model translator, which converts the Excel file into extensible markable language, which can be further processed, and the model then shows up in the graphical user interface. So all engineers have to worry about is learning and writing the equation in the Excel sheet. And there is extensive documentation which is available, which engineers can read, which is part of the SUMO software. So this language has been kept developed by keeping engineers in mind, and engineers can implement their own equations with a specific format in Excel, and rest of the job is done by SUMO. Now, what is there? I am assuming, like I said, everybody has looked at the software and has some understanding of how the interface looks like. So if you go to the SUMO software, the top view button tab, and if you click on that, there is a folder for directories, and then you go to install directories. From install directories, you are able to access all the model files which are present in SUMO. So you can see that it will open in a list of folders, and the two folders which you are interested in is the My Process Code folder and a Process Code folder. So if you open My Process Code folder, it will provide you 3 subfolders such as language, model base, and process unit. And if you open Process Code, that's where you will find an extensive library of extensive models which are present in SUMO, such as digital twin option, languages, model base, process units, and so on. And if you click on process unit, for example, you see there is a list of bioreactors, controllers, design tool, flow energy elements. If you click on one of these, let's say bioreactor, you can see that within bioreactors, you have multiple folders, such as CSTR, digesters, granular SPR, and so on. By clicking on a CSTR folder, you can see that all the files which are available are in Excel. And once you open these Excel, different sheets in this Excel guide you to implement different things which can help you improve the model or implement a model. One important thing to keep in mind is, although you have access to all the model library, the default model library, please don't try to modify the existing library. Use My Process Code folder and implement your models under My Process Code folder, so that you don't create issues in the current library, the default library, and you can use these as reference or templates. And if you install SUMO again, or if you install the next version of SUMO or a new release, then the My Process Code folder stays with your install or with your computer, so that you don't lose those files. Okay, so let's dive into a little bit of detail about these folders, which are under the process code. So you can see that we have 7 folders. The first folder is named Digital Twin. That is where you can actually implement your own digital twin in an Excel example. So SUMO has an Excel IO, which allows you to communicate with the SUMO file from the Excel sheet, which will allow you to create your own digital twin if you wanted to. You can implement new languages in this specific folder. If you want to add a new biokinetic reaction, improve the pH model, add more gas transfer, model base is the folder which you would be interested in. Under process units, like we saw, you have reactors, you have influent unit, you have clarifier, and if you are interested in creating one of those, that's where you would find them. The system setting folder allows you to access the system file in Excel, where you can add constants or molecular weight of compounds, or you can find unit conversions or add your own unit conversion if you need to. We also have a template folder where you can copy templates from to create these model files. And finally, the tools. So these tools, if you're familiar with SUMO, we have influent tool or aeration tool, which is accessible for SUMO users for influent characterization or identifying aeration specific parameters for modeling. You can create your own tools and then link them to different models. So all these are available in Excel within these folders, which one can modify or develop for their own specific need. Now let's look at some of the inside information of these 4 important Excel sheets. The first one is a system setting. So the system setting Excel sheet allows you to access to these sheets which you see on your screen. And I would point to a couple of them and give you an example. So the sheet where it says function, there you can define specific functions and equations which you can later use in model development in biokinetic matrices. Or you can define your own constants and you can implement your own unit conversions. So if you wanted to improve a unit conversion in SUMO, you wanted to add your own conversion, then you would add it in this specific sheet. This specific sheet. The next Excel is a process unit type. So you can see that in the process unit folder in the Excel, you will have these sheets. The first sheet is the help sheet, where a little bit of information is provided about the model development, about the model itself, the model structure, and you can use this model to include that information. The unit sheet allows you to add images to that specific model, add attributes, different model options one can use to select from the graphical user interface. Under the parameter sheet, you can define parameters for this model, which will appear in the input setup of the graphical user interface. Next is the code sheet where the equations are written. And then the last 2 important sheets here are display and pop-up. Display is what you would require to identify outputs which you want to see in your output setup in SUMO. And pop-up is that display board which shows up if you bring your mouse closer to a process unit. And we'll do a couple of exercises in which one of the exercises will focus on developing a new or modifying an existing process unit. The third one on the list is biokinetic model. So again, you have the help sheet where you can define information regarding the model. You can define the parameters in the parameter sheet. You can define the model structure, which is the Gujer matrix, and we will discuss this in a moment. Then you can look at the pH model. And then in the component sheet is the list of all components or the state variables. And finally, the last sheet allows you to include more calculated variable, such as total COD, which is made up of individual components, or mixed liquor concentration calculations, or oxygen uptake rate calculations. And finally, the fourth Excel sheet, which is part of a specific project, is the plant-wide calculation. In the help, again, you define what are you using it for or developing it. In the parameter sheet, you define the parameters, and then in the code sheet, you will implement the equations. Before we can do a biokinetic based example, it's important to understand the Gujer metrics, in which commonly the models are written. So there are two important rows, two important things you need to know about this table. In the rows, you get to define the rates, the stoichiometry, and in the columns, you define which state variables you are looking at and their elemental composition. So you can see in this example, you have three state variables: XB, which is a particulate biomass; SS, which is soluble substrate; and SO, which is oxygen. On the right-hand side is where you define the rates of the equation. Most of the time, the rates are governed by a Monod-based equation. And in a Monod-based equation, the rate of the reaction stays at maximum at high concentration. And when it gets to this half saturation value, or Ks, which we refer to most of the time, the rate of the reaction is halved. So the process rate is defined in this column on the right-hand side. And within each row, you define how the reactions are taking place, or how these state variables are converting from one to the other. Here, two fundamental processes have been included: the growth reaction and the decay reaction. One important thing to keep in mind is if one state variable disappears, the other appears or is oxidized. So overall, there needs to be a mass balance or continuity which needs to be achieved in a Gujer matrix. And this is part of the biokinetic matrix. The second important thing you need to learn about process units is how to write equations. This example which you see in front of you is of a CSTR reactor, where you have influent coming in and the effluent going out. So you can see these circular things which are defined as port in SUMO. So where the influent comes in is the imp port, where the effluent goes out is the out port. So you would define the ports, you define the symbol, you define the units, and then using this format, you can write equations where left-hand side of the equation is equal to the right-hand side of the equation. If I had to read this specific table, I would see that output ... Q, Q is the symbol of flow, is equal to what is written in the expression tab, which is input ... Q. Then I define my unit, and then I provide some comments, which is same as the output flow, same output flow as the inflow. And you can define your own calculations. So for example, under reactor hydraulics, you can create your own table and add, let's say, HRT calculation, which is included currently in the model, where you define the liquid volume and divided by the input flow to that specific reactor. So you can see in this case, it's just, you need to know the symbols, correct symbols, you need to know the format, and it's all about writing the left-hand side of the equation being equal to the right-hand side of the equation. Okay, so we are already close to our first demonstration. In this demonstration, we will be modifying an existing biokinetic model. So the exercise today is, let's say there is an industrial wastewater treatment plant which receives an unknown compound, and the user, and I mean the SUMO user, would like to include it in the model for their own client. So you have a client who is receiving an industrial wastewater which contains an unknown compound, and you would like to include that in the model and develop a model for your client. The existing structure of the model is presented on the left-hand side. So you have particulate, a substrate, which gets hydrolyzed in the model to soluble substrate, which gets biodegraded or oxidized in the model. You have biomass generation, and the substrate is oxidized. So the first thing you would do is you would try to characterize the compound which is coming in. In this example, let's assume it's a colloidal material, it's slowly biodegradable, and it's organic in nature. And based on our understanding of looking at the data and talking to the client, we have identified that this material or this colloidal material first gets flocculated, and then it gets hydrolyzed and biodegraded. So what we have to do is, first we have to establish a model structure. On the left-hand side, this is the modification we are looking to do. So we will include a new component into this model called CS. We will modify the structure to include a flocculation rate reaction where CS gets converted to XS, which is particulate. The second important thing you need to do in this exercise is to identify the correct stoichiometric relationship and the rate. And in this model, we are saying that the new component which we are adding, 1 gram COD per cubic meter of CS, which is colloidal substrate, which is organic COD, is converted to 1 gram COD per cubic meter of XS, which is particulate substrate. There is a flocculation reaction, which is governed by Monod equation and dependent on the excess concentration, meaning more particulate, higher is the flocculation rate. The two parameters which we need to define for the rate is KF, which is specific flocculation rate, and from data we identify it's 5 per day, and half saturation rate for CS, which is 10 milligram per liter. And on top of that, we will have to update our total COD calculation, which is part of the calculated variable sheet. So let's go and do this example. Now, I would go back to SUMO. I would click on View, go to Directories, and then straight away go to Install Directory. Now you can see we have 2 folders. My process code folder is where I would like to implement this new model. But I would use an existing model structure. So I would go to process code, go to model base, go to museum. And for today's exercise, I would use the ASM1 model and modify and include this colloidal new biodegradable substrate. I would simply copy this, go to my process code folder, go to model base, my model category, and simply paste. I would right click in this folder and go to properties just to make sure that this file can be edited. So I would remove this read only, apply, changes. So now I'm ready to modify this file. The first thing I would do is to rename the file. I would rename this to ASM1 industrial. And now I would open this up. I would enable content. Now we would go through these sheets and implement the model. So the first sheet is the help sheet. And you can see there are some instructions which have been provided on how to develop your own model. And I would recommend attendees to look at these help sheet before they start implementing the biokinetic model. In the parameter sheet is where you would define the 2 new parameters. So let's go and introduce those 2 parameters to begin with. I would simply start by copying this table. So I know that I'm keeping the same table format. I would rename this table and call it the header flocculation rate. Now I would need to define the new symbols which I want to include in the model. And in the in the presentation you saw, the first symbol I wanted to have was KF. I would make the F subscript. And the other one is KCS. The first one is the specific flocculation rate. I would enter a default value of 5. And what's important here is to identify the unit. And in this case, per day is the right unit. For the half saturation, I would rename this. For flocculation, and the value was 10, and the units was gram COD per cubic meter. So I would simply copy it from somewhere else, and that's it. So now you have created a table, a parameter table, a new parameter table in SUMO, which will appear in the user interface, which you will see. One important thing to keep in mind is once you create a table, you would want to link these cells to their respective symbols. So in this case, if I click on cell D4, on the top, you would notice that it says mu_a, which refers to this cell right here. But if I click on D12, then you can see that it does not refer to this symbol. So in order for me to provide a value and connect this value to this specific symbol, what I would need to do is I would have to highlight these cells and press Control M. And that's a macro we have created in SUMO to connect these 2 cells. So now if I click on this D12, you can see that K_F is the identified symbol for this specific cell. Okay, now if I click on the model, this is the Gujer matrix, which you guys saw in the presentation slide. I would before I make modification to this model file, I would go to the components sheet and add a new state variable or component to the model. So these are the list of components which are already existing part of the model. And I need to add one more new state variable. So I would simply insert a row underneath the soluble biodegradable organics. I would type in CS because we want to create a colloidal soluble substrate. I would make this a subscript and call it colloidal biodegradable substrate. Now I would need to provide values, which I assume for these specific process units, and they can be used in SUMO, either in influent for providing that as a default value for the influent unit, or it can be seed for other reactors. So in this case, I would say 40 milligrams is typically what's measured in the influent, and rest of them is a low value. And for now, I provide 1. And where it says non-detect, I would provide non-detect. And I'll simply copy rest of the important rows. And the units is correct because we're dealing with an organic COD. And then under the particle size, I would simply change it from S to C to assign it a colloidal nature. And similar to what we did in the parameter sheet, we need to assign a value to this specific symbol so that we can use it in the Excel for other model calculations. And right now, in this case, we are using the activated sludge column to provide values to the symbols. So I would simply select the first cell and the last cell and press Control M. And now if I have this cell highlighted, you can see on top it says C_S. So we have successfully created a new component, added and provided a value. Now before I move to model sheet, there is a check component fraction, because the number of components in this table must match the number of components in the model sheet. So I simply click on check component, and you can see it does not, because I still have to modify the model sheet. So there are 16 variables in the state variable sheet and only 15 in the model. So I'll press OK. I'll go to the model sheet, and I would insert a column in the same order right after SS and include that new symbol. And now if I go back to the component sheet and press check components, the check has passed. So the Excel sheet will guide you a bit in terms of if you're making mistakes and how to do the model development. Okay, so now what we need to do is we need to create a reaction, and we need to provide the elemental composition of this CS. At the moment, we said, okay, it's COD. It doesn't contain any nitrogen or any charge. And we would include a new reaction rate. So I would insert a new row, and I would make these numbers in order, and I would write rate of flocculation, provide a name. And now what we said was, if 1 unit of CS disappears, and the minus sign means that is removed from the system, then we need to make 1 unit of XS. So I would simply add 1. Now we have established a stoichiometry that 1 unit of CS disappears, 1 unit of XS is formed. But that is not enough. We need to provide the rate as well. And the rates are provided on the right-hand side column, as you must have noticed in the Gujer sheet in the slide. So I would simply make sure I have the rate unit, and then I would go back to the parameter sheet, just make sure that I use the same symbols. So I would define KF, going back to the model sheet. So KF, and then we said it's a Monod equation relationship, and it depends on the concentration of colloidal material and the concentration of particulate substrate. So a Monod equation will look something like this. And you can define these in calculated variable using a specific function and use that function right here. But for now, I will just simply define these as they are. Okay. So this is the Monod function, where KCS is the half saturation we just implemented in the parameter sheet. And then it's also dependent on the concentration of the particulate soluble substrate, because that's how the flocculation rate will change with the concentration. All right, and that's it. I would save this, and I would simply, before I move on, I need to do a check. I need to check the continuity, and I need to check the rates. So when I click on the continuity and the rates, it will go through the macro and look at the mass balance. It will go through each and every column. So in this case, you can see that I made a mistake, and it prompted that there is a mistake in U11. Please check FKF. I say okay, and you can see that I left it not to be subscript. So I'm simply gonna do a subscript, press OK, and do this check again. And this time, hopefully, if I did not make any mass balance error in terms of converting one compound to the other, and if I didn't make any mistakes in terms of naming the parameter, then this would happen. The continuity and rate check has passed. I would click OK. And if I scroll down, you would see that there are these green cells where it's calculating the mass balance. That means all the reactions are mass balanced, and we are ready to go. Now, the last thing we want to do is, because we added a new state variable, we would go to the calculated variable sheet. This is where you are including calculations which are actually measurements which you perform in the field. So for example, mixed liquor is actually what you measure, but mixed liquor is made up of different components. In this specific case, what we are after is, we are after improving the total COD concentration, because we just included one more component, which is colloidal. So I would go to this Excel sheet right here in the expression tab and simply add the new component. I'll make sure the symbol is correct. And right now, if you notice, the value for this total COD, which is shown on the right-hand side column, is 1830. And when I go to calculate, a macro is gonna run, make sure all the calculations are correct. And if it's correct, it's gonna show you a green. And the total COD, which we just included a new component in, you can see that the equation which shows on this value changed to include that specific variable. And now we are ready to go. So I would save this file and close it.
Anush, before going forward, just a remark. for the rate, in the rate expression, you have a typo with the brackets.
Okay.
Sorry to interrupt.
No, that's okay.
It's the,
oh yes,
the opening bracket. Yeah.
Yes. And just to be sure, I'll do this rate check again. Good catch.
It was not me, it was one of the listeners, but thank you, Akram.
Okay, perfect. So I would close this and I would close SUMO and I would restart SUMO. And what you would see as that specific model will now appear in SUMO and you would be able to use it. So I would create a simple plant just by dragging the influent, a reactor, a simple activated sludge plant, an effluent. I would recycle the sludge back. And I'm hoping everybody knows how to do this because you must have attended the old webinar or used SUMO in some level. Okay, I would simply go to the model setup. I would click on Museum, Focus and Custom Model. And you can see that there is a My Model category which now appears. I would click on that. And that's where your model is, ASM1. I would simply click and I would go back and you can say that see that the other model is ASM1 industrial. Now, if you look at the bottom panel on the left-hand side, you can see there is a flocculation rate, which we included. This is coming from the parameter sheet directly. So you can adjust these values to further calibrate. If I go to the input setup, and I click on the influent, another check you need to do is once you set up the file and you go to the input setup, the SUMO is going to compile and look for errors if there are any with the model. And if you made a mistake in the model, like we did, where the model prevents it from compiling, it will give you an error message. Okay, so we click on the influent and we click on the influent composition on the left-hand side. So now you can see we have colloidal biodegradable substrate, 40 milligram per liter, which we included as part of this model development. Now I can go to the output setup. I'll make a table and I'll specifically plot that state variable from the left-hand side. So, okay, you can see that's 40 milligrams. I would simply drag and drop the CSTR. And you remember one was the initial seed which we had provided in that Excel. I'll go to simulate and I'll press calculate steady state and it's done. And you can see that in the CSTR, the concentration of colloidal biodegradable fraction is changing. And if I would click on the, again, the output setup, and I can define the particulate, bring the particulate biodegradable organic as well. And I can look at the oxygen uptake rate as well. And I want to see, I just want to make sure that the influent, the new component which I included, is contributing to the oxygen demand. So I would go back to the influent. I would make this 0. I would come back. And before I do the simulation, the previous value is 867 milligram per liter per day of oxygen demand. And now you can see it decreased. There is no colloidal in the influent and nothing in the CSTR. And that's it. I can change the parameter to adjust the data and modify the model. And this is, guys, a simple example how you would create a model in SUMO. Now moving on to our second demonstration for the day, second and last demonstration for the day, is a process unit. So let's say you have an industrial client which on regular basis receives a influent which is specific characterization. So what we would do today is we would take the influent process unit from our regular library, and we would copy that and modify the image to look something like this, and add new defaults. Simply add new defaults, add new output setup and pop-up table. And these are the values which we are going to use. Okay, so let's do this. So I would go back. I would go to the process unit folder. Oops. I would go to the process unit folder, process code folder, sorry, process units. I would click on the flow energy elements. I'll click on influent, and then I'll try to copy 3 specific files. I'll copy the influent image. I'll copy the influent group, and then I'll copy the SUMO1 concentration-based influent file. Right click, copy. I'll go to the My Process Code folder, process unit, and I'll create a new folder here. And I'll call it Industrial Influent. I'll go inside that folder and paste this file. Again, before I begin modifying these files, I'll right-click, go to Properties, and make sure they're not hidden. They're not read-only files. Apply, okay. All right, so first thing I want to do is I want to rename this file. So I want to call it Industrial Influent. So I would use a short form. I would call it IND Influent. I would rename the image as well, IND Influent. And I would call this again, IND in Influent. The group info Excel sheet is very important, which would allow you to define what is your default value, default model. So in this sheet, you would go and you would say your default model for this unit is IND influent, because that's the name of the file. Save it and close it. Okay, let's work on the process unit model now. So once you open it up, there is a help section. You would say that industrial influent. You can provide more notes, which will be saved. Second thing you would do is go to the unit sheet. And you can see that there are various examples, various options or settings, but I would say that you can go to the documentation and review what each of these mean. Currently, what we will be interested in would be changing the image. So we will change the name of these files, which you see. So the default graphics is specifically the one we are interested in at the moment. So I would double click, and you remember we renamed it to Industrial Influent. So I'll simply change the name of this file. Then I would go to the parameter sheet, and these are the parameters which will show up in the influent. And if I go back to Excel, go back to my slide, what did we say? We said that our flow rate should be 240, total COD so much, and so on. So I would simply change the default values right here. 340, 55, and let's say the temperature of wastewater coming in is 28 degrees. So now I have defined total COD, TKN, total phosphorus to be these much higher values typically found in municipal because it's industrial specific. Other two fractions which we wanted to change were ammonia to TKN and ortho P to TP to 40% and 30%. So I'll go back to Excel. I'll scroll to the bottom. There they are. So I'll simply change this to 0.4 and 0.3. That's it. And save it. Now, if I click on the code, and I can call this industrial specification. If I change the header as well, the new header will show up in SUMO. I'll simply go to the code sheet, and I don't need to make any changes here, but you can see that the equations are written in terms of left-hand side being equal to the right-hand side. And these parameters are either defined in the parameter sheet, or they can use the one defined in the previous row. I'll go to the display, and display is what will show up in the output setup. So let's split this table up into two sheets, two tables. So I would simply copy this header, and right here, I would insert the copied table. And I can rename this one and call this industrial specific for industrial frequently used variable. Now, in the output setup, I'll have two tables instead of one frequently used table, which will show up. I would go to the pop-up sheet. I would do the same for the general as well. So I would I'll copy this general header, insert this folder. I can rename this and call this industrial general. And that's these symbol values are what will be available in SUMO for me to plot or use. Again, going over this in the display tab, these are the values or symbols which you need to know. But you can simply insert variables in this, which will show up in the output setup of your simulator. Okay, I would save this file. I would close this. And again, I would reopen SUMO. And hoping I did everything right, that file would show up as a separate category. Oh, maybe one thing which I need to do before we go through this exercise is changing the image. So I already created an influent unit. In a PowerPoint, I would simply change the color to be dark so that I can distinguish it. Maybe I can change the inside as well. Let's go with this one. So I would right click and I would save that image in that specific folder. So I would save it in the SUMO 19, my process code, process unit, industrial influent folder, which I just created. And from the type of the extension of the file, I would click and select .enf, and I would replace this file. Now I'm ready to go back to SUMO and see what happens. So I'm going to reopen SUMO. And now you should have a new process unit category with the new model, with new defaults, and a new image. I would go to the configure. You can see at the bottom there is industrial influent, which we just created. I'll simply drag it over. You can see that it's a different color, which we just created. I would bring the regular influent, and I'll combine the flow. So we can look at how it's mass balancing. Okay, I would simply go to the input setup, And when I click on the industrial influent, you can see the defaults are what we had provided. You can, on the left-hand side, see the name of the table is also changed. Industrial influent specification, which we provided. If I click on influent fraction, the fraction of ammonia to TKN and fraction of OP to TP is what we had provided as default. So in this way, you can simply create your own industrial unit with specific default for your client or your model. I would go to the output setup. I would create a quick table just to verify that my calculations are working. You can see when I have industrial influence selected, I have this industrial frequently used variable, which I had created, a new header. I can simply drag that over, and you can see that these are the correct values which I want. I would do the same for the influent. So you can see the values are different because they're a regular SUMO default. And then I would click on the effluent and drag and drop. And you can see that the calculation, if I would do a mass balance, you would see that these would be the new values which I would get in the effluent after combining these two streams. And now I can go to simulate and do steady state calculation or dynamic run for my project. And that's it. So one more thing. So in output setup, like you saw, if I click on industrial influent, we had this new header. If I bring my mouse, you can see that we created the new industrial general for this unit. And that was from the pop-up sheet. So now you can see how easy it is to, each sheet serves a purpose in these model files. And if you change something in the parameter sheet, it shows up in the model setup. For process unit, if you change something in the parameter sheet, it shows up in the input setup. If you change something in the code sheet, it's the equations behind. In the display, it will show up in the output setup. And pop-up, if you change something in the pop-up, it will show up in these pop-ups, which are everywhere with each of the process units. Okay, so going back to the slide. So in summary, we are an open process source software. SUMO has accelerated innovation by promoting process model development. So you can investigate your own new processes. You can implement new technologies which are up and coming for your clients for improving the design. It's very, very engineer focused. So you can see that I did not do any C++. All I needed to know was where everything is, what the format is a little bit, and then left-hand side is equal to the right-hand side. And you don't have to worry about writing, like I said, programming to make it into a graphical user interface. You create a model in Excel, it shows up in the interface. It helps you improve your in-house knowledge, so you can create these process units for your in-house testing, and it can provide competitive edge. You know, we have many clients who have been developing these for utilities. And when the project goes into hands of a different consultants, they can see that these process units are coming from another consultant and not from the software itself, because there is a lot of in-house knowledge. This helps you better provide the client support you need. Okay, well, I thank everyone for listening in today. Like I said, the slides and the video of this session today will be provided to all the registrants. And hopefully we were able to answer most of your questions in the chat window. But if you still have more questions, feel free to write us at support@dynamita.com. Thank you very much. And I would end this session in next 30 seconds, unless there are more questions which are being answered in the chat window. Okay, guys, well, thank you so much for attending and have a wonderful day.
Thank you, Tanush. You too.